Hello, Chem 213 students, and welcome back for our second lecture this week about carboxylic acids and carboxylic acid derivatives. When we left off last time, we were talking about various reactions that could be used to produce carboxylic acids. One of those here being shown as the Grignard reaction with CO2, which starts with the introduction of magnesium to bromobenzene in the presence of an ether here as a solvent, producing the Grignard reagent, and then finally a reaction with carbon dioxide in order to produce benzoic acid. Once we have a carboxylic acid, we can convert these into a variety of other functional groups. For example, we can reduce the carboxylic acid to a primary alcohol with exposure to the reducing agent lithium aluminum hydride, followed up by an acid workup to protonate the carboxylate ion that is ultimately produced by this reduction. So this reduction proceeds through a intermediate in which a hydride ion is formed from the lithium aluminum hydride. And remember, that's generally the way that reduction with a aluminum hydride or borohydride occurs. The aluminum here has a negative formal charge, and it's going to want to give up that hydrogen. And when it does, that is going to leave as a hydride ion. So note that this is very different from a proton transfer, in which a proton leaves with no electrons. In this case, the hydride leaves as a hydride ion, in which case you've got the you've got both of the electrons coming over with the hydrogen. And so in this case here, what we've got is we've got the two electrons from the hydride ion attaching themselves to the hydrogen. And so it's a proton transfer in the sense that the proton is leaving the carboxylic acid, but not in the sense that a proton is leaving the aluminum hydride. Instead, it's leaving with two electrons. Those two electrons are going to be used to make a bond to the hydrogen, and that will produce hydrogen gas, which will ultimately drive this reaction forward because the hydrogen gas, if the hydrogen gas is removed, which it is quite easily for a gas, then it will drive, by Le Chatelier's principle, the reaction will move forward in order to replace that removed hydrogen gas. Now, the reaction finishes here with the two electrons that were in the bond to the hydrogen being left on the oxygen, producing the carboxylate ion, and you get a carboxylate salt with the lithium ion here. Then left over is the aluminum and the three hydrogens. Now that these electrons are lost, the aluminum no longer has a negative formal charge. The aluminum here with three hydrogens. Aluminum is group 3 with 3 valence electrons normally, so if you do its formal charge and give it 1 dot from each bond, it's got 3 dots, right? So 0 formal charge now. Whereas over here it had 4 dots, so that's 1 extra dot compared to its normal 3 valence electrons, giving it that negative formal charge. And so remember that when you're using aluminum hydride or borohydride, you're going to be really giving up a hydride ion here. And this is something we've seen previously when we talked about the reductions of aldehydes and ketones as well. Now, this is not the end of the reaction here, though. At that point, we have the aluminum hydride, and it goes through this pericyclic type mechanism here, where we end up with the pi bond here between the carbon and the oxygen, instead going and being used to create a sigma bond between the oxygen and the aluminum. And then the hydrogen here is now going to essentially be transferred into creating a bond here with this carbon like so. And so now at this point, we've broken this bond between the hydrogen and aluminum. The hydrogen is now bonded to the carbon atom. The carbon atom has 4 bonds and no lone pairs, so it has 0 formal charge. And now we can have the loss of a leaving group here, and that leaving group will be the oxygen attached to the aluminum hydride. This is going to occur in such a way that we have this resonance arrow here, which reforms a carboxyl group, a carbon double bond oxygen here with the carbon, and the leaving group leaves. And ultimately, we have a carbon that's double bonded to an oxygen, and we have that hydrogen that came from the aluminum hydride, giving us an aldehyde. Now, that aldehyde can be further reduced. We'll still have aluminum hydride in the reaction mixture. So again, remember the way the aluminum hydride functions is that it gives a hydride ion, meaning both of these electrons in the bond between the aluminum hydride come with the hydrogen and are used to form a bond with this carbon. Now, this carbon cannot make 5 bonds, so we will also draw this resonance arrow to represent the lone pair of lone pair of electrons being on the oxygen atom, giving it 3 lone pairs and 1 bond, thus a -1 formal charge. And at that point, we have 2 hydrogens attached to this carbon, giving it 4 bonds and no lone pairs, and no formal charge there. Finally, we need to complete this reaction. We don't want to finish with this negatively charged product. This has to be protonated to become more stable. And so we finally work up in a second step. After this is all done, we work up with an acid. Note that we could not have an acid in this step, right? No acid here. This has to be a second step. So this is the second step of the reaction. We have to take out the aluminum hydride first because the hydride ion is a very strong base and would thus deprotonate the acid and even deprotonate water itself. So we certainly could not have this acid introduced in the step where the reduction is occurring, but it's reduced in a subsequent step, or it's added in a subsequent step, which is something that you've probably experienced in one of your recent labs as well, where you did one day where you produced a deprotonated ion, but then the next day you can't come back and protonate that ion by the introduction of a strong acid. So here, any strong acid here will give you the hydronium ion in water, so it'd have a proton transfer here, thus giving this oxygen now a bond to the hydrogen, a bond to the carbon, 2 bonds and 2 lone pairs, no formal charge. And now the water, of course, has lost its proton. It's no longer hydronium, it's now water. And that is the reduction of the carboxylate, the carboxylate group here, the carboxylic acid, to a primary alcohol. Notice that it's primary. There is only one other carbon attached here. Now, lithium aluminum hydride is quite a strong reducing agent, so it will reduce whatever carboxyl group that you've got. If you want to be selective about the reduction of the carboxyl group without reducing another group, for example, this ketone over here. So we look in this this example down here. We've got a ketone, a benzyl ketone here, and we also have a benzyl carboxylic acid. So now if we have a carboxyl group like this and we use borohydride in THF, of course, to stabilize the borohydride, recall that from the alcohols chapter 12, will then reduce the carboxylic acid to a primary alcohol. But if you have got an aldehyde or a ketone group here and you use the borohydride, you can just selectively reduce the carboxylic acid so that it becomes a primary alcohol. And again, in the reduction, note what occurs. We basically add 2 hydrogen atoms here and lose the oxygen atom, right, in this reduction. It's kind of a double reduction. And so here we can see we now have a bond to a single bond to the oxygen, and we have 2 hydrogens here instead of the carboxyl group. So an interesting thing about carboxylic acids is the way their reactions occur is significantly different from those in ketones and aldehydes, in the fact that we can replace the OH group here on the carboxyl carbon with other groups. And so that's going to produce for us what is known as a carboxylic acid derivative. And so essentially here what we've done is, replace the carboxyl group and we reduce to a primary alcohol here. Notice that we've got a change in oxidation state when this occurs. This is a reduction. But carboxylic acids can undergo many reactions in which there is no change in the oxidation state of the carbon atom. The OH group here is simply replaced with another group, leaving the carbon in essentially the same situation, where it's double bonded to an oxygen and then bonded to something else that is likely to also be electronegative as well, giving it the same more electronegative than the carbon at least, giving it the same oxidation state here, neither an oxidation nor a reduction. Z here means some kind of heteroatom, meaning not carbon. So we can replace this with the OH group here with a variety of groups without changing the oxidation state in the carboxylic acid. There are a number of common carboxylic acid derivatives. Acid halides here are like an acid, except the OH group is replaced with a halogen atom, like a chlorine or a bromine. We can have a so-called acid anhydride. This is called an anhydride because in the process water is lost. Anhydride meaning no water, basically, taking out water. And we can get a kind of double ester here, which we call an acid anhydride. We can have an ester where the OH group is replaced with an OR group, R being some carbon atom. Or we can have an amide in which the OH group here is replaced with an NH2, or this could be other carbon atoms as well instead of hydrogen. All of those would be referred to as amides. Any compound where the carbon has 3 bonds to an electronegative atom is a carboxylic acid derivative. So notice that chlorine, oxygen, and nitrogen are all electronegative atoms. And so they're all kind of, pulling electrons away from this carbon atom, preserving this electrophilic center here. We also have, so for example, we could have reactions to produce a nitrile as well. And so this is a kind of name that you should become familiar with when you have a group attached to a carbon atom that is triple bonded to a nitrogen. This is called a nitrile. In terms of the stability of carboxylic acid derivatives, there are several factors to consider in the stability of carboxylic acid derivatives, but the primary one is how easy is it for you to go back and produce the carboxylic acid from the derivative that you made. It will be most easy to produce that derivative if this group that's been added can leave very easily. So we know that groups that have a negatively charged oxygen atom, such as hydroxide or methoxide or any alkoxide ion, these stabilize the negative charge okay, but not all that great. You would rather, a better leaving group would be a leaving group like water, which would leave as a neutral molecule instead of a negatively charged alkoxide ion. So when it comes to esters and amides, these tend to be quite stable compared to acid halides and anhydrides, because when the halide leaves, it leaves as a chloride bromide ion, which has this large electronegative atom, stabilizes the negative charge quite well. Also, if it's leaving as a carboxyl group itself, if you look at if you have an anhydride, the leaving group is going to be some carboxyl group like this one here. And this will have a better stabilization of the negative charge due to the fact that there's resonance here between these two, right? And so we can see that these are all examples here of esters, and these esters are quite abundant in nature due to their relative stability, such as methylbutanoate, which is the flavor of pineapple, the primary flavor component, isopentyl acetate here, the primary flavor component of banana, and butyl acetate, the primary flavor component of pear. So you'll see that a lot of these esters too have nice tastes and smells. When you have artificial flavors, like artificially flavored banana, what they do is they chemically produce this isopentyl acetate. You might notice that it's not exactly the same flavor as a banana. It's because there are many other subtle flavors in a banana, but the isopentyl acetate is the primary flavor component of banana. That's true with grape too. I love artificial grape flavor. I don't think it tastes like a grape, but it is the primary flavor component of grape, but there's lots of others. Now proteins are particularly stable, and this is because they're produced by dehydration reactions of amino acids, which contain a carboxylic acid and an amine group, which react with one another to produce amides. And these amides are particularly stable. And so, all of our structures, skin, hair, and so forth can be made from these, and they're not going to be super reactive, which is good. We want them to be relatively stable, and we want our skin to stay right where it is, right? There's lots of other compounds in nature that have amides in them. For example, melatonin, a sleep hormone here, that is produced when your body is getting ready to go to sleep. It also has an amide. Recall again, an amide is a carboxyl group, C double bond O, with the carbon also attached to a nitrogen atom. So, for all these carboxylic acid derivatives, how will we name them? Well, if you've got an acid halide, you just replace the ic acid in the name with il, and then the halide here. So here this would be referred to as ethanoic acid, or common name acetic acid. We would just change the ic acid in ethanoic or acetic acid and change it to ill bromide. So acetic acid would become acetyl bromide. Or again, here we have benzoic acid. If we want to have the acid chloride where the OH group is replaced with a chlorine, we'd call it benzoyl chloride. So just replace the ic acid with ill chloride, ill halide, whatever it is. Remember that if we have a ring attached, we just call the ring by its name, such as cyclohexane, and then we say carboxylic acid. So if we have, instead of the carboxylic acid group here, we have an acid halide group, we call it cyclohexane carbonyl chloride here. So we replace the carboxylic acid, the part in red here, with carbonyl chloride. If we have an anhydride, we replace the word acid with anhydride. So if we have two molecules of acetic acid, produce the anhydride, and we'll go into this reaction in more detail later. But if you have two acetic acid molecules reacting, what's going to happen in this reaction, just not talking about mechanisms here, but very simply describing where the atoms go. If you look at where the atoms go, essentially you're going to lose a water, and then this oxygen will be attached right here, and that's what you see here. The oxygen here gets attached to the carbonyl carbon. And so that's the reason why they call it an anhydride, because you lose water when this is produced. And so we simply replace the name of acetic acid, the acid part, with anhydride and call this acetic anhydride. Now, if you have a dicarboxylic acid, this can react with itself in this dehydration reaction that we've seen right here to close a ring. So again, we'd be losing water, which would include this, and then this oxygen would go and attach itself over to this carbon right here, and we'd end up with 1, 2, 3, 4, 4 carbon atoms. So we got 1, 2, 3, 4, and here it is 1, 2, 3, 4, with 1 and 4 being the carbonyl carbons, and then there's an oxygen between here. So again, if we call this is its common name, not its systematic name, its systematic name would be butane dioic acid, right? Butane dioic acid in the format that we discussed previously in naming these. Its common name is succinic acid, so we'd call this succinic anhydride, or we could call it butane dioic anhydride as well. When you have anhydrides that are asymmetrical, so here, it's not necessarily the case that you'd have two acetic acid molecules reacting. Let's say you had an acetic acid and you had, one with a benzene ring attached, right, like that. Now you get a asymmetric anhydride where one side is different from the other, and that's exactly what's going on here. If we have the acetic acid reacting with the phenylacetic acid, we would end up with the acetic benzoic anhydride. So here, where this comes from is this part is called the acetic part, and I called it phenol here. What I meant was benzoic acid, so benzoic acid here, the carboxylic acid directly attached to the benzene ring. So this was the benzoic acid part, and they reacted to make the anhydride, and so we call it acetic benzoic anhydride. In terms of esters, esters have a very unusual way of naming. So what you do when you look at an ester is you see that you're going to have on one side the oxygen atom here, on the other side the carbon atom. Okay, and so what you look is you look at where the carbonyl is, and you divide this into two parts. You have the part that is the carbonyl with the oxygen atom, and then you have the part that's attached to the oxygen atom that's circled in green here. Uh, and so what we do with the part that has the carbonyl with the oxygen is we name it by the same name as this part here. To some extent, we can call this ethyl here, ethyl group, acetate, the derivative of the acetic acid. Here we have malonic acid, a diacid. If we put ethyl groups here in the place of the hydrogen atom, we'd call it diethyl malonate. So we end with 8 here. See that? We end with 8. Ethyl acetate. Malonic acid, we replace the ic acid with 8. 8 here. And so that's the way that esters are named. Here's another example with an ester that has the other style of naming where we have the cyclohexane and then we say carboxylic acid, cyclohexane, carboxylic acid. Here again we would look, and this would be the methyl group here, and then this would be the rest. So this is just going to be called methyl, but here instead of calling it cyclohexane carboxylic acid, we're going to call it cyclohexane carboxyl 8. So we replace the ic acid with the 8, just like before. In terms of amide, again, it's a similar thing. We take the ic acid here and we replace it with something else. So if the OH group here is replaced with an amide group, or here with a nitrogen attached to the carbon with double bond, so the OH is now a N with something attached to it. We replace the ic acid and we say amide. So this is acetic acid again. We replace the ic acid and say acetamide. Or if we have benzoic acid here, we replace the oic acid here with amide. So we say benzamide. We don't say benzoamide. We just say amide. So again, yeah, amides are going to be replacing the ic acid or oic acid with the word amide. So here, if this were an OH group, we'd call it cyclohexane carboxylic acid. Here instead, we're going to replace the ic acid with amide, so we'll call it cyclohexane carboxamide. Now, one thing that can happen when you have an amide is there might not be an amide with the nitrogen attached to only hydrogen atoms. Sometimes you might have other groups attached, like here we have a methyl group attached. So what we do here is we name it first as if it were a hydrogen with acetamide, but then we add something to the beginning, and we say N, meaning that this methyl group is attached to the nitrogen, and then we say methyl, N-methylamide. If you have more than one group, you'll say N twice, just like if you were using a locant, 1, 2, 3, 4, in normal naming. So here we'd say NN dimethylamide, meaning acetamide rather, meaning that both of these methyl groups are attached to the nitrogen atom that's part of the amide. And then it's acet because of acetic acid. This would be acetic acid if we're an acid with 2 carbon atoms, and then amide. When it comes to nitriles, so nitriles are also carboxylic acid derivatives. It's a little bit different. You're not just replacing the OH group. You're taking this carbon and making it triple bond to a nitrogen and attached to no oxygens. But it's still a derivative of acetic acid here. So again, if we have acetic acid and we replace this carbon with a carbon triple bond nitrogen, we take out the ic acid and we put in nitrile, O-nitrile. So acetonitrile. Benzoic acid, here we replace the oic acid with O-nitrile. So if the carboxylic acid group is replaced with a nitrile group, we say benzonitrile instead of benzoic acid. Then that is the naming of the various common carboxylic acid derivatives. So they would just basically name it the same as the carboxylic acid, but replace the ic acid with the ending that corresponds to that carboxylic acid derivative, with the exceptions of the esters, which are a little bit more complicated, right? And we just end with the 8, carboxyl 8. Okay. Now, in terms of the reactivity of the carboxylic acid derivatives, so remember that one thing that I thought was that I was indicating was important was the quality of the leaving group. So a good leaving group is going to really, really make this much more reactive. And so here we can see a chloro group, if it leaves, it's going to leave as a chloride ion. So the leaving group here would be the chloride ion when it leaves. And we know that halide ions, due to their large size and high electronegativity, stabilize the negative charge quite well. Second to that would be in terms of reactivity, would be the the anhydrides. So for the anhydrides, these these products here, these leaving groups, are stabilized by the resonance here, and so that makes these pretty good leaving groups too, better than just an alkoxide ion. So that's a better leaving group than, for example, here, if this leaves, we have an alkoxide ion. That's not so stable as a leaving group, right? The oxygen can stabilize the negative charge better than a carbon, sure, but it's not a particularly stabilizing for the negative charge. It's really going to be quite reactive, quite basic as well. And then in terms of, and you can think about this in terms of the conjugate acid, right? The conjugate acid would be an alcohol. Alcohols are not particularly acidic. Their pKa's are quite high, in the upper tens. So this is going to be a pretty strong base by comparison. Now, when it comes to this leaving group, this would be NH2, a nitrogen with 2 lone pairs and 2 bonds, giving it a negative formal charge, rather than having 3 bonds and 1 lone pair, which would make it 0 formal charge. This is extremely basic, and when we're using, when we're looking for our strongest bases, we're usually talking about hydride ion or amide ion. They're the conjugate acid. So the conjugate acid of this, so if we had the conjugate acid, an alcohol, we're talking here pKa's of around 15 to 20 or something like that, depending on all these other things, induction, resonance, and so forth. 15-ish. Here we're talking about a pKa of more like 5-ish for the conjugate acid. And here we're talking about negative pHs, negative pKa's, right? For these guys, like negative 4 or something, 4 to 7. And then for the amide, its conjugate acid has a pKa of around 38 for ammonia. So here we're talking about, again, NH3 here would have a pKa of 38, super high. So not a great leaving group at all, a terrible leaving group. So what this means is that the acid chlorides are going to be very reactive because they produce stable products here that stabilize the negative charge, whereas the amide is super unstable, and so these amides are going to be less reactive. And as we discussed, in protons, these are produced from amide bonds, which we call peptide bonds when it comes to proteins. And that's great that these are stable, because we don't want these hydrolyzing very easily. We don't want them breaking apart. We want those bonds to stay in place to preserve the structure of the proteins that make up our body. Also important are induction and resonance effects, as you can see here. If we had more electron withdrawing atoms, that would even help to make it an even better leaving group by induction. Sterics is also an issue. How can this leaving group leave? How can the nucleophile attack? But primarily, we can understand this this relative reactivity here in terms of the quality of the leaving group. So if we take a look here and take a look at acyl chlorides, we're going to go down each of these factors here and consider these. When we took at acyl chlorides, these are going to be the most reactive. In terms of induction, the induction here does produce for us kind of pseudo resonance structures here as well because of the electron withdrawing effect here of the chlorine. The electronegative chlorine enhances the electrophilic character of the carbon. So what this means that the fact that the chlorine group is pulling electrons towards this makes this more negative, and of course you have the oxygen here also pulling electrons this way. So that makes this carbon right here particularly partially positive, making it more reactive with potential electrophiles to initiate the reaction. In terms of resonance, the chlorine atom does not donate much electron density to the carbonyl, but it does a little bit. So here, for example, we can draw a resonance arrow of a pi bond between two atoms of differing electronegativity, and so that puts an oxygen here with 3 lone pairs and one bond giving it a negative formal charge. This carbon now has 3 bonds and no lone pairs, so it has a positive formal charge. So now we have a lone pair adjacent to a carbocation, which results here for us in a resonance arrow that we can draw here, indicating a pi bond between the carbon atom and the chlorine. Now the chlorine should have, to have 0 formal charge, it should have 3 lone pairs and 1 bond like we see here, but now it has 2 lone pairs and 2 bonds, so it's essentially lacking an electron from the lone pair, giving a positive formal charge, and the oxide continues to carry this negative formal charge. We say this is not a significant contributor, and you can see why, right? Having a positive formal charge on a atom with high electronegativity is not favorable in terms of resonance structures. So amides are the least reactive acid derivative, and we can evaluate this by those 4 factors listed before, or by the factors listed before. In terms of induction, the nitro atom is less electronegative than chlorine or oxygen, or it's about on par with chlorine, slightly less, but definitely less than oxygen. So if we're considering that, the nitrogen will be withdrawing some electron density from the carbon, but not as much as if you had a more electronegative atom, such as chlorine. And the resonance here, the resonance is with the nitrogen atom, it can contribute a significant electron density to the carbonyl carbon, as we can see from these resonance structures. So again, we have a pi bond between 2 atoms of differing electronegativity. So we can draw this resonance arrow giving the oxygen 3 lone pairs and 1 bond, and the carbon with 3 bonds and no lone pairs here, so they have formal charge. And now we have this lone pair on the nitrogen, which is delocalized in the amide because it is a lone pair here adjacent to a carbocation. And again, this is not a particularly significant contributor in the end because the nitrogen here is making 4 bonds with no lone pairs, giving a positive 1 formal charge, and having a positive formal charge on a electronegative atom is not particularly stable. But you can see here that the nitrogen atom contributes significant electron density to the carbonyl. And what does that mean? Well, that means that this is not as positive as it would otherwise be in an acid chloride. So aldehydes, so there's one thing, a huge difference here between the reactions that we're learning in this chapter for carboxylic acids and those that we learned related to aldehydes and ketones. So carboxylic acids, aldehydes and ketones are also electrophilic, but they don't undergo substitution in the same way, and that's what we saw in the last chapter. Whereas with a carboxylic acid, we can do substitutions of the group on the carbonyl here. So it's because in these carboxylic acid derivatives, the group that is attached to the carbonyl can leave as a leaving group. If you have a hydrogen and it's the leaving group, hydrogen leaving as a leaving group would be a hydride ion. This is extremely reactive. The hydrogen does not stabilize this negative charge well at all. if you have an R group, you're leaving, like let's say with CH3, for example, if that's your R group, you're leaving with a negative charge in the carbon atom. According to REO, A being atom, these are terrible atoms for stabilizing a negative charge. And their conjugate acids, if we're talking about CH3 here, CH4 rather, it's conjugate acid, this would have a pKa of around 50. Hugely not acidic, right? It's hugely not acidic. So this makes this a very strong base, very reactive. Same for hydrogen. Its conjugate acid would be hydrogen, pKa, very huge. This is hugely basic, highly reactive as well. Um, Now, carboxylic acid derivatives, they can undergo these substitutions because when the leaving group leaves, if you have, for example, if this is a chlorine, your leaving group is a chloride ion. Whoops, I'll put that up here. Chloride ion, that stabilizes a negative charge fantastically. And so this is the reason why carboxylic acid derivatives can undergo nucleophilic acyl substitution, as it's going to be called, and ketones and aldehydes cannot, because their leaving groups would be terrible. However, the leaving groups on these carboxylic acid derivatives will at least be okay in some cases. Not in the case of amide, but if it's an acid chloride or an acid anhydride, it certainly will. So how is it that these nucleophilic acyl substitutions go? Well, it's really quite simple. Again, you've got this carboxyl group, and by now you know with these carboxyl groups, you've got this charge separation here where the oxygen is quite partially negative, the carbon is quite partially positive. So if you've got some kind of a nucleophile, this nucleophile is going to go in and it's going to attack that positive carbon right there. Now, carbon cannot have 5 bonds, so we draw this resonance arrow of the pi bond between two atoms of differing electronegativity, and then are able to put the lone pair on the oxygen, indicating a negative formal charge here. Now, at this point, what would normally happen, with a nucleophilic reaction with an aldehyde or ketone is that the oxygen would then be protonated and you get the alcohol. However, in this case, we have a great leaving group. So instead what happens is we have these lone pair electrons, and we can then use these to reform the carbonyl bond while simultaneously the leaving group leaves. And the leaving group will leave because in these acid derivatives, carboxylic acid derivatives, we have leaving groups that are pretty good leaving groups here. So this is the mechanism. The nucleophile attacks the carbonyl. You get a tetrahedral intermediate, and then finally the leaving group leaves and the carbonyl is regenerated. And again, this cannot happen with hydride or carbon containing negative ions, because these carbanions and hydride ions are terrible leaving groups, but our chlorides and carboxylate ions are quite good leaving groups. So for example, here let's say our nucleophile is methoxide, and we have an acid chloride here. So again, we have the nucleophilic attack at the electrophilic site here on the carbon that's partially positive, loves electrons. Simultaneously, we get this resonance arrow here showing the lone pair on the oxygen, giving it a negative formal charge. And then after that's complete, then we have a loss of the leaving group that occurs, reforming that carbon double bond oxygen, and now giving us an ester rather than an acid chloride. So chloride is, and it is going to be the chloride that leaves too, because chloride is a fantastic leaving group, whereas methoxide would not be. The oxygen only stabilizes the negative charge somewhat. It's important to note that this is not an SN2 mechanism. So remember that SN2 mechanism, so this is not this. Because remember that SN2 mechanisms mean a bimolecular mechanism that occurs in a concerted fashion in one step. This is not a mechanism that occurs in one step in this way. It occurs in 2 steps. We have the nucleophilic attack, the generation of a negatively charged oxygen here, and then a subsequent process that involves the loss of the leaving group. In some cases, we'll want to do a proton transfer in the mechanism. This often depends on the conditions under which the reaction is occurring. If the reaction is occurring in an acidic environment, we're going to probably start with the protonation of the carbonyl, which, as we've learned in the last chapter, enhances the the electrophilic nature of this carbon and makes the carbonyl even more reactive. Under basic conditions, you're not going to have protons to protonate the carbonyl instead, so you're not going to have these positively charged structures form. Instead, you'll have the immediate attack of the nucleophile on the carbonyl that is not protonated. But in the end, you'll often have to deprotonate the nucleophile that attacked. So for example, let's say that our nucleophile is water here, okay, and we're doing this under acidic conditions here. So here, since this is acidic conditions, this would begin with the protonation of the carbonyl. So we'd have, we'd have a hydronium ion here, like this, and we'd start with this protonation. In fact, this is going to be shown on the next slide, but we'd start with this step, and then we'd have, after that, in the next step, we'd have the protonated oxygen, which now has one lone pair and 3 bonds, so it's positive in formal charge. We still have the ester part of the group here, but then that would follow up with an attack by water, neutral nucleophile here, and we would ultimately end up with a situation where we would then have the alcohol immediately, and we'd go straight to here, and then we'd have the loss of the leaving group that occurs as well. Okay, so let's show the actual mechanism. So this would be under acidic conditions. So all the participants in the reaction mechanisms should be consistent with what's employed. So the first step will not be the nucleophilic attack. So as I said, the first step has to be the protonation, not the nucleophilic attack. Why? Well, if we did the nucleophilic attack first in this way, we would have a negatively charged alkoxide ion, which if there's first of all, we end up with a positively charged water here and a negatively charged oxygen. This kind of situation is highly unstable. So we'd have a huge activation energy for this. In addition, if we have acid available, this acid is just going to protonate this alkoxide ion and end the reaction immediately. So we're not going to have an immediate attack of the nucleophile under acidic conditions. Instead, what will happen is we'll begin with the protonation. So we'll have a protonation of the carbonyl, and we saw this in the aldehydes and ketones chapter 2. The advantage of this is not only is it possible that this can occur under acidic conditions, but also this is going to produce for us an even more electrophilic center here, where the nucleophile really wants to attack right in here. It's really attracted to this because we've got even more positiveness in this region. And so after we've protonated the alcohol, now we have the nucleophilic attack by the water. So now the nucleophilic attack occurs, and again, carbon cannot have 4 bonds, so we draw this resonance arrow for a pi bond between 2 atoms of differing electronegativity, or actually there's a pi bond right next to this positively charged oxygen too. So at that point now we have the water attached, and this water is a neutral nucleophile, so it is protonated after it attacks. And in terms of the stability, this stability is much greater for this positively charged oxygen here. Still not particularly stable, but far more stable than the situation we had here, where we had more formal charges, a negative and a positive formal charge. Here we just have this positive formal charge on the oxygen. So this intermediate is much more stable, and this production of this intermediate will be much faster due to this much smaller activation energy here that occurs on the first step here, rather the second step, I guess, the nucleophilic attack of the water. Now, if you're doing this under basic conditions. Under basic conditions, the first step will be the attack of the nucleophile. First of all, hydroxide is a much better nucleophile than water due to its negative charge. And so that's going to allow this reaction to occur more easily. When we go back to water here, water is not a great nucleophile. It doesn't have a negative charge. It's not as prone to attacking the carbonyl as well. But something with a negative formal charge will be very attracted to this partially positive carbon here. Remember, we have this huge charge separation. This partially positive carbon will be attracted to this negative nucleophile, and we'll have the nucleophilic attack and the simultaneous resonance arrow here. This leaves the oxygen with 3 lone pairs and 1 bond, giving it a -1 formal charge. And again, here, this is not going to be a reaction that is energetically prohibitive, because the oxygen, although it's not the greatest stabilizer of the negative charge, it's much better than having a lot of other formal charges, and also oxygen isn't so terrible at stabilizing the negative charge due to its high electronegativity. Now, when the amine is a nucleophile, it will attack the carbonyl first, without the carbonyl being protonated. Now, this is due to the exceptional, basicity of this amine. It's considered a weak base, right? So this is like being under basic conditions. When you're introducing ammonia, you should think of this as being like under basic conditions. So it's going to behave in such a way that you were in basic conditions. Because if you introduce acid, you're going to protonate this ammonia anyway. So the nucleophilic attack will occur without protonating the carbonyl, and we'll get this similar intermediate. We do have this kind of not so great high formal charge. That's to be sure, right? But still, the fact that this is basic means that it wouldn't operate well under acidic conditions anyway. So just be sure to avoid drawing an intermediate with 2 charges of the same type when drawing these types of acyl substitution mechanisms. So it's not the most stable intermediate, and this reaction isn't going to go as easily as the others for that reason. But it's going to occur under basic conditions, so it will be like the basic conditions here that we had with the hydroxide. So we are going to have proton transfers in these mechanisms, but where the proton transfers occur depend on the conditions of the reactions, whether the conditions are acidic, neutral, or basic. So you're going to have to decide for yourself, based on the conditions, when the proton transfer will occur. So let's say we're looking at this reaction. We're going to have the reaction of this acid chloride with water produce an alcohol and HCl. So the conditions are not acidic, so we're not going to be protonating the carbonyl. So it's going to be the nucleophilic attack that occurs first. Again, water's not a great nucleophile. This is probably not going to be the fastest reaction, but this is the only way that it could occur, given that we're not starting with acidic conditions, so we're not going to be protonating the carbonyl. We'll have a subsequent loss of the leaving group. And what that's going to do is, because we have a neutral nucleophile, though, that leaves this oxygen with a positive formal charge, because after the nucleophilic attack, the oxygen is making 3 bonds and has 1 lone pair for a positive formal charge. So then the chloride is lost as a leaving group, great leaving group, so that's what drives this reaction forward. Finally, though, we've still got this positive formal charge even after this lone pair comes down and is drawn again as a carbon double bond oxygen. So to produce a stable neutral product, we'll have to have the water come in and deprotonate this proton from the positively charged oxygen, and then we will regenerate our carboxylic acid. Now, the leaving group does not require the protonation in order to leave, but there is a proton transfer at the end here, and that's the take-home message here. Is that since we have this neutral nucleophile attacking, it's going to end up with this positive formal charge, so we do have to deprotonate it at the end to get the stable neutral compound. So this pattern, we're going to have this pattern typical for all reactions of acid halides. So under acidic conditions, we would have a proton transfer. This was not acidic conditions, so we didn't have the proton transfer. Thus, we started with the nucleophilic attack. After that, there could be a proton transfer before the loss of the leaving group, not in this case. Then we have the loss of the leaving group, which in this case was the chloride ion. Finally, because we had this neutral nucleophile attacking, in this case we had to deprotonate it with a final proton transfer here. So an acid chloride, you may recall from previous chapters that we had used SOCl2 here in the production of these chlorides. This is also a nice source of the chlorine atoms for this. It will produce SO2 gas, which will leave as a gas driving this reaction forward, and HCl. And this will produce for us our carboxylic acid chloride. So this mechanism comes in two parts. So let's think about this thionyl chloride here. The thionyl chloride has a bond between sulfur and oxygen. Oxygen is significantly more electronegative than sulfur, so we end up with a situation that's quite similar to our carbonyl, where the sulfur here is nucleophilic, and the only electrons really that are easily lost here are the pi electrons, and so that is going to be what provides the electrons to initiate this reaction, and then we'll have this resonance arrow here indicating the electrons being on the oxygen atom. So at this point, the sulfur has 4 bonds and 1 lone pair. It has 0 formal charge because if we gave it its dots here, if we count these dots, these are 6 dots, and sulfur is in group 6, 6 valence electrons. So this is 0 formal charge here. This oxygen now is still making 2 bonds with 2 lone pairs, so it has no formal charge. What's occurring here is the oxygen, we could draw this as a positive formal charge on the carbon, 3 bonds and no lone pairs. The other way we can do it, though, is we have a lone pair adjacent to a carbocation at that point, so we can draw a resonance arrow here indicating instead a carbon with 4 bonds and no lone pairs, so no formal charge right here. And now this oxygen has a double bond to the carbon and a single bond to hydrogen, and so it has 3 bonds and 1 lone pair for a positive formal charge. This oxygen here on the thionyl chloride now has gotten the electrons from the pi bond. It has 1 bond and 3 lone pairs, so it's negative in formal charge. At this point, we can have the loss of a leaving group, chloride, great leaving group again. So we have this resonance arrow again, putting the lone pairs now in this pi bond, and then we have immediately the loss of the leaving group. At this point, our sulfur is again here at its 0 formal charge state. So is this oxygen, now having 2 bonds and 2 lone pairs. This oxygen here continues to be at the positive formal charge state. And so to produce a neutral product, it's going to have to be deprotonated at some point. So we're going to have a proton transfer where the chloride grabs the proton here, and then these electrons are left behind, leaving this oxygen as 2 bonds and 2 lone pairs, so 0 formal charge. Again, the chloride is a good leaving group. So is the thionyl chloride here. This is an excellent leaving group because the charge is like stabilized here by this inductive effect of the chlorine combined with a resonance effect. This is similar to the resonance effect in a carboxyl ion. Like if this sulfur were carbon, you'd have the resonance here. It's the same thing. So that makes this a great leaving group. The combination of the inductive effect here of the highly electronegative chlorine, along with the resonance here between these oxygen atoms and the sulfur atom, make this a great leaving group. So at this point, we can have a nucleophilic attack by the chloride and get the acid chloride. So now we have this great leaving group here, so we can have this nucleophilic attack on the carbon that's in the carbonyl. Again, we have the resonance arrow here to put the electrons on the oxygen, giving it 3 lone pairs, 1 bond for negative formal charge, and then we have the loss of the leaving group, and ultimately we get our carbonyl back. uh, and we can do some. Ultimately, too, we got this this negative formal charge oxygen, and so we can draw a resonance arrow here, turning this to a pi bond to the sulfur, and simultaneously the loss of chloride, which we know is a great leaving group, which gives us sulfur dioxide. And the removal of this sulfur dioxide as a gas then drives this reaction forward. When reacted with water, we can convert an acid chloride to a carboxylic acid. So again, here it depends how it's going to go depends on the conditions that you have. As we saw before, if we have the nucleophilic attack of the water and the resonance arrow here, we get this oxygen with a -1 formal charge. This is followed up by a loss of our excellent leaving group chloride ion, giving us a protonated alcohol here because of the attack of the neutral nucleophile water. And so the last step is for the water in the solvent here to deprotonate this and ultimately produce our carboxylic acid from the acid chloride. So as we can see here, that's what we showed in the mechanism. We react water with the acid chloride, we get the carboxylic acid. HCl here is a byproduct of the hydrolysis. So here, because we lose the chlorine group here, so pyridine is usually used to neutralize it. This keeps the conditions not acidic, so the reaction continues to go in the same way. So if we have some base, like some amine, specifically pyridine usually, this will be protonated by the carboxylic acid, and you'll get this, basically this amine salt here, pyridinium chloride as it's called. If you react an acid chloride with a alcohol, you're going to get an ester. So remember, the acid chlorides are the most reactive, right? They're the most reactive of these carboxylic acid derivatives. So the most reactive ones will react to produce the less reactive ones, and the less reactive ones will stick around, right? When you're remembering that, just keep thinking of your proteins in your body. They have the amide bonds, quite stable, which is a good thing, right? You don't want them reacting. The acid chlorides here, very reactive. They will go ahead and react with an alcohol. This alcohol will be the nucleophile will attack right here, and then you'll have the resonance arrow, and then ultimately you'll have the second step where the leaving group leaves, and you'll end up with an ester. So the ester is the second most reactive type of acid chloride. When you have sterically hindered alcohols, it can cause them to react more slowly because they do have to get in here and do the nucleophilic attack. So the more sterically hindered that they are, the slower that's going to be. So if we have here, we have a dialcohol here, a diol, and in this diol we have a secondary alcohol and we also have a primary alcohol. When it comes to how the reaction is going to go, it's going to be the primary alcohol that does the nucleophilic attack because it's just easier for it to get in here and do that rather than a secondary alcohol which has a lot of other things hanging off it which may get in the way of its approach to the acid chloride. But ultimately, it will make the ester that attaches here, this oxygen, not this one over here. Now, in terms of the acid chlorides and reaction with amines, so we know that our amides are the most stable of these. So we can react the acid chlorides, which are less stable, with ammonia or some amine to produce an amide. We can react either with ammonia or with a primary amine with the nitrogen attached to one carbon, or a secondary amine with the nitrogen attached to two carbons. So here, and you can see it takes two equivalents. We'll see why that is the case. But the acid chlorides are used to synthesize amides. Pyridine is not used in this case. Instead, we use an amine because amine is also a base. It's also an amine, so we just have a second equivalent here to mop up the proton at the end. So it's a similar reaction. There's no difference in the mechanism. It's the same mechanism. We just don't need we don't need pyridine at the end. We already have amines that can grab the protons. Acid chlorides, again, the most reactive of these carboxylic acid derivatives. This can be reacted to produce a alcohol by reduction. So same way as we'd produce it from the carboxylic acid, we react with excess lithium aluminum hydride in the presence of water to ultimately protonate the alcohol at the end. And again, we do need the water to provide the protons in there. We need an acidic workup, as it's called. So remember, we can't have an acid. We can't have any acid here in this first step because what we're using is hydride ion to be the nucleophile and attack. And of course, we have the resonance arrow here, like we saw before. And this hydride ion would be protonated and be turned to hydrogen gas if there were any protic solvent or acidic conditions. And then we have the resonance arrow going back here and making the pi bond between the carbon and the oxygen, and the simultaneous loss of the leaving group chloride. At that point, we have an aldehyde, so we can undergo a further reduction. We reduce the aldehyde further. Again, we have a hydride ion attack, and we have the resonance arrow to the oxygen, giving it a negative formal charge with 3 lone pairs and 1 bond. And then finally, we need one more step, and that is to protonate the alkoxide ion that's produced, and that is done by acid. A lot of acids would work here, or even water to some extent. And we get the primary alcohol from the acid chloride. Essentially the same reaction we observed with the carboxylic acids, right? The reduction of the carboxylic acids. So you don't have to remember this as 2 separate mechanisms. It's pretty similar mechanism. They have a lot of similarities, right? So if we use a particular a particular type of aluminum hydride that has all these sterically hindered oxygen groups here, these big tert-butyl oxide groups here, and 1 hydrogen, we can stop the reduction of the aldehyde here instead of going all the way to the primary alcohol. And so this reagent will be more selective with the acid chlorides due to steric hindrance here. It won't do a second, so it won't do a second attack here. Once this has been done, it's not going to do like that. So it's not going to do this due to the steric hindrance. Okay. So some other reactions of acid chlorides, again, we can use other nucleophiles. For example, we can use a nucleophile that is the Grignard reagent here. Okay, the Grignard reagent is written like this. And again, like usual, it's the R group here. That's the nucleophile that's going to go in and attack. And so we write this as R. It could be CH3, it could be methyl, it could be ethyl, it could be other things. But similar type of mechanism. We're going to have the nucleophile attack here. We'll have the resonance arrow to the oxygen. We'll have the subsequent resonance arrow returning, reforming the carbonyl and the simultaneous loss of the leaving group. At that point, we're going to get a ketone, but we're still going to have the carbonyl group. So we're still going to have an electrophilic center right here where the carbon is. So the Grignard nucleophile can attack again. We have the resonance arrow here going on to the oxygen. And then finally, we have the alkoxide ion that's produced. That's not a stable product. So we do need a subsequent acidic workup here to provide the proton that will ultimately protonate this. And we get we get the addition of 2 of these R groups here and the formation of this alcohol right here in this process. Another type of reaction that these acid chlorides can undergo is a reaction with what's known as a Gilman reagent, or also a lithium dialkyl cuprate. meaning lithium here being a cation, um, the cuprate ion being the anion with the copper attached to two alkyl groups here. The Gilman reagent adds only once to the acid chloride, so it's going to stop here. Notice that when we use the Grignard reagent, we end up adding two alkyl groups and getting an alcohol. Whereas if we use the Gilman reagent, we get a similar reaction, but instead of adding two alkyl groups and getting an alcohol at the end, we only add the one alkyl group, like this methyl group here, and we retain the carbonyl. Uh, and the mechanism for this is I think, often when they don't include them in the book, it's because they're not completely understood. It's probably something similar to what we saw with the Grignard reagent, but not quite the same. Um, Finally, this is a summary of the reactions of all the reactions of the acid chlorides that we discussed. They all generally follow the same mechanism where you have some nucleophile attacking the carbonyl, and then we have a subsequent step where we have a negatively charged oxygen here, and then the carbonyl is regenerated, and in the second step, the chloride is lost. What differs is just whether the conditions are acidic or basic, and and also which nucleophile is being used. Is it an alcohol, which will require an amine for an ultimate deprotonation at the end? If you react with amines here, they are their own amines. You just use excess to equivalents, and you get the formation of various amides. Here you get an ester. If you react with the strong reducing agent here, lithium aluminum hydride, you'll get a primary alcohol. You follow up with water. And the way to remember these is to think about the mechanism, right? You're going to have this deprotonated alkoxide ion. You need a workup step with water to protonate that. If you want to stop at the carbonyl and not reduce all the way to the alcohol, what you're going to want to do is use a reagent here, which is highly sterically hindered. So the OR group here, big groups hanging off of the aluminum with one hydrogen that can reduce once. And then you have a subsequent acid workup again for the same reasons that we had with the aluminum hydride. You can also have a reaction with a Grignard reagent as a nucleophile, in which case you'll add two of your alkyl groups and ultimately end with a tertiary alcohol here. And if you want to, again, if there's an alternative, if you don't want to react all the way to the alcohol, you can add one alkyl group and just stop at the ketone here if you use the Gilman reagent. And finally, if you want to regenerate your carboxylic acid from your acid chloride, you simply need to react with water to change the chloro group here to an alcohol group. Remember, you're going to need a base to ultimately deprotonate that neutral nucleophile water that attacked. And if you want to take the carboxylic acid and return it to a acid chloride, you would use SOCl2. And that's going to conclude our lecture here for this week. I welcome you to try the homework problems. This was kind of a long lecture. I did not stop it in the middle like I had intended to. So just if you want to take a break in the middle and try some homework problems, go right on ahead. And I highly suggest that you stop at the end of 20.6, do some homework problems, and then go back and do 20.7 and 20.8 after that. I hope you have a great week and great weekend, and I'll see you next time. Bye-bye.